Good morning, everyone.
Good morning, sir. Sir, am I audible?
Yeah.
Should I start?
Yeah, please.
Okay, thank you. Okay. Good morning, all, and welcome to the final day, which is day 5 of online ATAL FDP on machinery conditioning, condition monitoring. Today's technical talk is on condition monitoring of gearboxes by Professor Anand Parey from IIT Indore. Dr. Anand Parey received his B degree in mechanical engineering from MIT's Gwalior in 1998 with and MTech in maintenance engineering from MANIT Bhopal in 2001. Dr. Parey has earned his PhD degree on gear fault diagnosis using vibrational analysis from IIT Delhi in 2005. He served as a lecturer at BITS Pilani, Goa campus during the academic session of 2005 and 6. Dr. Parey has got postdoctoral fellowship at University of Alberta, Edmonton, Canada during the session 2006 and 7. He has been he has worked as a manager in the capacity in Compton, Greece, Mumbai, and Larsen & Toubro again in Mumbai during 2007 and 9. Dr. Parey has joined IIT Indore in August 2009 as assistant professor in discipline of mechanical engineering. Currently, Dr. Parey is working as professor in IIT Indore. His research interests are in the areas of mechanical systems, signal processing, gear fault diagnosis, noise and vibration isolation, and condition monitoring. Dr. Parey has published more than 50 research articles in reputed international journals. He has produced 6 PhD students and currently guiding 5 research scholars. At present, he has sponsored projects worth rupees 150 lakh. He has done many industrial consultancy and testing work in the field of condition monitoring, signal processing of mechanical system, and noise and vibration. So, with this, I would like Dr. Anand Parey, sir, to start your talk. Over to you, sir.
Thank you. Thank you very much for nice introduction. And I'm feeling very happy and honored to be with all of you. And as already mentioned that I would be going to discuss on gearbox fault diagnosis, okay, for next 2 hours. So it's a long duration, okay. So we can make it very interactive, okay. And I have a couple of presentations. So I mean, depending on the time, if time allows, then probably I will go for dynamic modeling of gearboxes also, okay. So let's see how it goes. So I can share my screen. Okay. So is my screen visible to all of you?
Yes, sir, it's visible.
Okay. Okay. So I would be presenting mainly on fault diagnosis of gearboxes. Okay. But before that, I think already the other speakers, they might have covered about condition monitoring and vibration monitoring. But I would be again briefly cover those topics, okay, and then we'll go to gearbox fault diagnosis. So you can see like gearboxes are employed in a number of applications, okay. So I have shown here just one application, which is a helicopter gearbox, okay. So the purpose of showing only helicopter gearbox is that this is a very critical in any helicopter, because you have just one gearbox, and I mean there is nothing like anything which is uh, working as a parallel system to that. Okay, so one engine and one gearbox. Okay, not like in aircraft where you may have some two engine kind of thing. Okay, so I mean the reliability of a gearbox is very important. Okay, so if it fails, so unexpected breakdown can result in downtime. I mean, for this particular case, it will be uh, a catastrophic failure, and I mean, human life and everything is at risk. So this is why, I mean, gearbox fault diagnosis is very important, not just for helicopters, but for any machinery. Okay, because unexpected breakdown can result in downtime of machinery and considerable amount of loss. So basically, this is condition monitoring. When we say it is basically a maintenance strategy, okay, and you might be aware of various maintenance activity, I mean, strategies like breakdown maintenance, preventive maintenance, and predictive maintenance. Okay, so I think uh, breakdown is something which when machine fails, then you have to replace the component and you have to keep it in order. So I mean that is as such not a maintenance, but something. Uh, I mean you have to do it. Okay, uh, because of the failure you cannot run the machine. Okay, in preventive you are doing some activities. Okay, whether the machine is in good condition, or I mean you don't know the condition exactly. Okay, and according to the OEM, okay, you have to basically perform some of the maintenance activities. So that is preventive maintenance. Like I mean the example of any uh, car or two-wheeler. Okay, if you are having any vehicle, then okay, you take it to the workshop at regular interval. Okay, according to the instructions given by the OEM. Okay, so then that is a good thing, because you, by that, if you are doing preventive maintenance, your downtime may reduce, but sometimes you are doing, I mean, you are overdoing the things. Okay, so that is how, I mean, the concept of predictive maintenance came. Like you should know the condition of the machine, and then based on the condition of the machine, you have to perform the maintenance activity. Okay, so that is basically known as predictive maintenance. Okay, so this is also known as condition-based maintenance, because now we are doing the maintenance based on the condition of the machine, and because we are predicting the, I mean, the performance and the condition. So that is also known as predictive maintenance. Okay. Since the potential breakdown of a machine is predicted through regular condition monitoring, and maintenance is carried out at the optimum time. So this is the philosophy of condition-based maintenance, that if the condition of the machine is deteriorating, then you start performing, or when you expect that, okay, by this condition monitoring technique, if you can predict that this machine is about to fail, or I mean some fault is about to develop, or it has just developed, okay, so then you need some corrective measures. So this is what is known as predictive maintenance or condition-based maintenance. So obviously it has many advantages as compared to uh, breakdown maintenance or preventive maintenance. Okay, but it requires access to reliable condition monitoring technique. Okay, so this is how uh, I mean uh, yeah, this is, you can say, when you are doing this condition based maintenance, then definitely uh, you have to have some technique. Okay, and if you are saying that there is some technique, it means you need to have some equipment and some uh, maybe some additional manpower is also required sometime. Okay, so condition monitoring of machine is not only able to determine current condition but also gives reasonable predictions of remaining useful life. So that is another advantage. If you are calculating the remaining useful life, then you can plan various maintenance activities. Okay, so or when you have to replace, or suppose you have to order a new machine, so those kind of activities can be done if you are aware of this remaining useful life. So that is actually a different topic, but that also comes under condition monitoring. So a predictive maintenance program can minimize unscheduled breakdown of all mechanical equipment in the plant and ensure that repaired equipment is in acceptable machine condition. Okay, so definitely if you are doing maintenance based on the condition of the machine, then the chances of unscheduled breakdowns are very less. Okay, so in that way, availability of the plant increases. So whatever I have mentioned in condition monitoring, it is basically you are assessing the condition of machine. So how you are doing that? So for that, you need some parameter, okay, or some signature which will give you the information of the condition of the machine. Okay, so it is very important to select the right kind of parameter. So how you can select that parameter? So yeah, obviously, if you are selecting any parameter, it should indicate the machine condition. Okay, deterioration. If it deteriorates, then its value should change. Okay, so you have to identify such parameters, and then once you identify that particular parameter, then you have to uh, basically measure it. Okay, at some regular interval or at on continuous basis. Okay, so this is known as if you are doing it continuously, if you are monitoring that parameter continuously, then that is known as online condition monitoring. But if you are taking the given parameter at some regular intervals, then that is known as offline condition monitoring. So whatever the case may be, you have to collect the value of that chosen parameter, okay, and then over a period of time, how it is changing, that you have to monitor. So you can see in this graph where you have uh, on x-axis runtime and on y-axis condition deterioration. Okay, so here you are basically you can see that initially, you may get this kind of graph or some other graph. So suppose you are performing condition monitoring. If you have applied condition monitoring for a given machine, okay, and then uh, you are collecting the signal and that particular parameter you are calculating. So suppose you get this kind of graph. So here you can see initially there is not much variation in the amplitude or value of that particular parameter. Okay, so this is almost constant. So you can say that machine is in good condition. But if you observe that there are, the chosen parameters amplitude is increasing, okay, so definitely some fault is developed, okay, and if you don't do any corrective action, then it keeps on increasing, okay, and then ultimately it fails, okay. So if you are monitoring the condition of the machine and if you are observing the trend, okay, so this is known as trend analysis, then you can tell, okay, that there is some fault which has developed, and before reaching to alarming situation or shutdown situation, or because failure definitely not acceptable. So you have some lead time, okay, so you have some time to take any corrective measure if you are doing it. If you are not doing it, then you will not come to know what is the condition of the machine. Okay, so this is how condition monitoring is very helpful in finding the condition, and based on the condition you are doing the maintenance. So in general, condition monitoring system is used to detect faults in machines, anticipate breakdown, and diagnose the problem. So you have to, as soon as, I mean, so this is the first thing that you have to detect the fault, that if there is some fault has initiated, okay. So that is very important. As early as possible, if you can detect the fault, that is very good, okay. And then anticipate the breakdown. I mean, how much time will it take to failure? That is also part of condition monitoring, because it gives you some time to react, okay, and then diagnose the problem. So you need also need to, I mean, know the root cause, or what is the main reason for that particular fault. So this is all required, and I mean that can be achieved by condition monitoring. So as I already mentioned, that you need to select a particular parameter, okay, which is basically giving you the condition of the machine. I mean, based on the, if there is some change, then that particular parameter should change. So there are various parameters like vibration, temperature, acoustic emission, shock pulse, sound pressure, stator current, then oil monitoring, and then field signature mapping. So there are many condition monitoring techniques based on the signature. Suppose you are capturing the vibration signal, then that technique is known as vibration monitoring technique. Okay, so acoustic monitoring, acoustic emission monitoring, or uh, shock pulse, okay, or thermography if you are measuring the temperature. So there are various techniques which are available, but as far as mechanical systems are concerned, okay, uh, they are mostly having at least one rotating component, and because of that, uh, the vibrations are there, okay, and if you monitor the vibration, then a lot of information about the machine condition can be obtained. So yeah, I already mentioned that online means you are doing it on continuous basis, okay. So this is how uh, but if you are doing, I mean, some research, or if you are doing it for some new machine, okay, so it is always better to do the modeling of that system, and then you perform some experiments, and then uh, various, I mean, nowadays because of the automation, you need to do it using some uh, artificial intelligence technique. So I mean, all these things are coming nowadays for condition monitoring of any system. Okay. So vibration based condition monitoring depends on two basic facts: that all common failure modes have distinct vibration frequency components that can be isolated and identified. Okay, so this is why, I mean, you can connect the frequency component of the vibration signal with some failure. Okay, and the amplitude of each distinct vibration component will remain constant unless there is a change in the operating dynamics of the machine component. Okay, so this is like amplitude will also change. Okay, so frequency and amplitude, these are the two things. If you are observing them, then probably you can know what is the condition of the machine, or some fault is developed. Okay, so mostly time domain analysis or frequency domain or time frequency analysis, this is done, okay, uh, for condition monitoring using vibration. Okay, so this discussion is mainly focusing on vibration. Okay, so how you measure the vibration, that is also important. So of course you need an I mean, basically you need some sensor. Okay, so in vibration monitoring, accelerometer is used. So accelerometer is the most commonly used transducer, and they are mostly seismic type. Okay, and they measure absolute vibration of the objects to which they are attached. Okay, so basically, if you see, I don't know how many of you have used an accelerometer to measure the vibration signal. Okay, but if you have used it, I mean, you basically fix it on the surface for which you are measuring the vibration. Okay, but what is inside the accelerometer? How many of you have, I mean, aware of it? I don't know, but basically, if you cut it, okay. So if you, I mean, you can see like this. Basically, there is one piezoelectric element. Okay, that is very important because that is converting your mechanical energy into electrical energy. I think you must be aware of what is piezoelectric element or crystal. Okay, so this is used in most of the accelerometers. Okay, and when you are using this piezoelectric element, okay, and this is the must thing. Okay, and then there is a spring mass system basically. So this uh, spring is a spring is used and mass is used to apply force on this piezoelectric element. So when you put it on any vibrating surface, okay, so depending on the displacement, okay, and the frequency of that vibrating uh, surface, okay, the force is being applied on this piezoelectric element and corresponding current is being generated. Okay, so this is how it works. So that is fine, but important thing here is because you are having a spring mass system, okay, which is vibrating. So this is single degree of freedom system, and it is, I mean, there's a force. I mean, this is basically, I mean, we are not considering damping over here, but damping is also there. So single degree of freedom damped system excited harmonically. Okay, suppose I mean you write an expression for that and then you solve it. Okay, then you will find that for a given frequency range, the response is flat. Okay, so whatever is the natural frequency of this single degree of freedom system, so that you can calculate using the stiffness and the mass, so which is under root k by m. So that will give you the natural frequency of this accelerometer. So that is important because once you know that natural frequency, so 1/3 of that will give you, I mean, the flat response. That is important because if you are measuring any frequency which is greater than 1/3 of the natural frequency of the accelerometer, then there will be amplification. Okay, so I mean, it can be, I mean, if you derive and I mean, if you just solve the equation, then you will, you can verify it. Okay, so in as a thumb rule, you can say that if you want to measure the vibration, okay, of any machine, then you must know what is the frequency range for which you are going to measure the vibration. Okay, so then you can ask how will know that what is the frequency range. So for that, I mean, you need to know at what RPM the machine is running and if there is any gear or if any bearing is there. So what all components of fan or what all components are there. Okay. So depending on the various mechanical components, okay, and its input speed, you can find out various frequencies which are associated with these input frequency. Okay, so and their harmonics also, 3 or 4 harmonics you can take. So if you talk about mechanical systems, so most of the mechanical system they may have frequency range from say 10 hertz to 5000 hertz. Okay, so you need a flat response to measure that range of frequency. Okay. So at least 3 times of this frequency range. Okay, I'm not saying that always it is 5,000, but you have to just uh, first analyze your system. Okay, what is the frequency range? Okay, or I mean, what are the various frequency components you can expect from that machine? Okay, so once you know that frequency range and whatever is the upper limit of that frequency range, so at least 3 times of that you should take as the natural frequency of the accelerometer. Okay, so this is how you can select the right accelerometer. Okay, so I'm just explaining it because it is very important to uh, to fix the right kind of accelerometer. Otherwise, whatever measurement you are doing will be incorrect. Okay, so condition monitoring program, if you are applying, its success will depend on the what kind of data you are capturing. Okay, so if you are capturing the wrong data, then probably your analysis will be wrong, and there is then you will give wrong conclusions. So that is even dangerous, even more dangerous. Okay, so this is how like it is very important for vibration monitoring. Okay, then when we say we are doing, condition monitoring or mechanical system, so mostly you will experience unbalanced misalignment, mechanical looseness and rubbing, damaged bearings, damaged gears, damaged fan blades, pump problems. Okay, so these are the basic mechanical components we will find in any mechanical system. Okay, so how you can find out, okay, these kind of problems. So that is, I mean, like you can find out like, so I mean, you are basically capturing the vibration signal using accelerometer. Okay, and then once you capture that signal, then as I already mentioned that you have to find out its frequencies. Okay, because there is a relation between frequency and some of any fault which is going to develop. Okay, so see for unbalance, okay, or if you are basically capturing the vibration signal, and then if you find that in frequency domain the rotational frequency component is quite high, okay, mainly in radial direction, then you can very easily conclude that some unbalance has developed. Okay, and that has to be rectified. Okay, so as such in any mechanical system which is having rotating component, you will have some unbalance. Okay, but over a period of time, if it increases, then this FR component will increase. Okay, so this is just one problem which you can identify. So basically you are capturing the signal and converting it into frequency domain, and then you are observing various dominant frequency component or characteristic frequencies of that system, and then you are observing them over a period of time how they are changing. Okay, so if you observe that FR, it means rotational frequency component is increasing, as well as 2 times FR is also increasing. Okay, and 2 times of FR is higher than FR. Okay, or the rotational frequency. Sometimes it is also called as 1x, 2x. Okay, so if 2x is greater than 1x or x, whatever you call, okay, then you can say that there is misalignment. So how, this is one way of doing the things. Okay, then you have to see if there is subharmonic components like 0.5 FR, and number of their harmonics are present, then it is mechanical looseness or rubbing. Then oil whirl is at 40 to 50% of FR, And if you have rolling element bearing, okay, so you have to calculate these characteristic frequencies like outer race, inner race, rolling element. So these frequencies you have to calculate and you have to see, okay, that how these frequencies are changing. So even if you have a good bearing, okay, or if you just installed a new bearing, all these frequencies will be present, okay. So and the equations are given, which is basically based on the number of balls, rolling element, diameter, pitch circle diameter, okay. So these things are and its contact angle. So based on these parameters, you can calculate uh, various frequencies which are associated with rolling bearings. Okay, and then if any one of them or maybe two frequencies like outer race or inner race at the same time they are increasing, or one at a time it is increasing, then you can say there is some fault which has been developed in the outer race or in the inner race or in both outer race and inner race. Okay, so then if you are gear, okay, if your system is having gear pair, so you have to calculate the tooth meshing frequency, okay, which is the number of teeth on a given gear, okay, and what is the RPM of that gear, okay. So number of teeth multiplied by RPM of that particular shaft and divided by 60 will give the gear tooth mesh frequency. And you will also get the side bends, which are n times FR, okay. So whatever is the rotational frequency plus multiplied by uh, n, which is the number of gear teeth plus minus k times FR. Okay, so suppose you have a gearbox which is having pinion is having say 50, say 60 teeth, and gear is having 120 teeth. Okay, so and if pinion is rotating at 100 RPM. Okay, so 100 into 60 divided by 60 is your gear mesh frequency. Okay, or if you are taking 120 teeth, then 120 multiplied by 50 because the RPM will be half. Okay, so whatever you take, it will come the same. So say for example 60 into 100 divided by 60, which is 100 hertz. So that is the gear mesh frequency. Okay, then plus minus 100 is the RPM. Okay, so it means 15 hertz. So plus minus 15 hertz. So you will find side bands at 115 and 85 roughly. Okay, so this is how if you see these frequencies in the gear spectrum, okay, and then you have to observe how it is changing, then you can probably come to know whether the gear is getting damaged or some fault has developed. Okay, so this we will discuss in detail in today's discussion. And then if you have some fan, okay, and so you have to see what is the blade pass frequency, and then if it changes, then you can say, okay, there is some problem in the fan. Similarly for pumps also, because in pumps also you have vanes. So number of vanes, depending on that, you have to find that frequency. Okay. Anyway, so this is how normally in industry people are doing vibration monitoring to find out the fault. Okay, so although I will be discussing more on gears and gearboxes, okay, but here rolling element bearings are also integral part of gearbox. Okay, so you cannot find any gearbox without bearing. So you also need to know what is happening in the bearing. Okay, so rolling element bearing is one of the essential element of the rotating machinery. And one of the important issue in rolling element bearing application is the reduction of noise and vibration originating from these bearings. And these bearings generate vibration during operation, even if they are geometrically and elastically perfect. So anyway, there is some misconception sometimes that if there is a good bearing or good gear, then there will be you will not find that particular gear mesh frequency or outer race frequency. No, it is always there because it depends on the configuration of this bearing and the gears. Okay, so here if you see uh, for rolling element bearing, okay, so characteristic frequencies will be there. And when some defect, okay, so you need to know, okay, if you are doing condition work, then you must understand, like if there is bearing, then what sort of faults it may develop. Okay, so like localized defects and distributed defects you will find in any bearing. So localized like crack, pitting, swelling, and dents. So these things you will find in bearings as localized defect. And then you have distributed defects like surface waviness of outer race, surface waviness of inner race, surface waviness of rolling elements, and then also off-size rolling elements. So these are, you can see that what is inner race. Okay, so inner race spall, then outer race is having some spall, then ball with spall, there is some crack in the outer race, then indentations caused by dirt. Okay, so these kind of faults will be present. Okay, and then if we know about these faults, then we can understand okay how it will affect the vibration signal. And then when we talk about waviness, then these are very exaggerated views. So these inner race and outer race, they may have some uh, I mean undulation kind of thing. So this will also generate different kind of vibration, and if it increases, then you can find it in the frequency domain. Okay, so this is all about defects in the bearings. Okay, now we come to gear fault diagnosis. Okay, so in gears also you may find various types of failure like scoring, wear, pitting, and tooth fracture. So these can also be classified as initial scoring, moderate scoring, destructive scoring, frosting. Okay, and wear like adhesive wear, abrasive wear, corrosive wear, and then pitting you have some subsurface, original failure, initial pitting, destructive pitting, case crushing, and then initial pitting, destructive pitting, tooth fracture. So, these kind of faults are present in any, they may develop in gearbox. Okay. So we'll just try to see like scoring, how it looks like. Okay. So scoring is due to the combination of two distinct activities. First is lubrication failure. And because if there is failure of lubrication, okay, so lubricating film, if it is not present, okay, for some reason, then there will be metal to metal contact, and it will cause some scoring. Okay, so some part of gear tooth will become very shiny. Okay, so this is scoring. Then where various types of wear is available, like adhesive, abrasive, and chemical. So a surface phenomena in which a layer of metals are removed or worn away more or less uniformly from the contacting surface of the gear teeth. So this is how, I mean, you can see where is change, I mean, modifying the tooth profile. Okay. And if in gears, if there is any deviation in tooth profile, okay, so it will change the vibration level, okay, and associated frequencies also. So this is how, I mean, we must understand various types of defects, okay, how they are modifying uh, the healthy gear, okay, and then what is the effect of those things on the vibration spectrum, okay. So how pitting is going to change the dynamics of the gear, how crack is going to change the dynamics of the gear, okay, and how the wear is going to change the dynamics of the gear. So, I mean, you need to understand first about the fault and what it is doing to the gear, okay, or any mechanical system, and then how it is affecting the vibration response, and ultimately you can find it in gear spectrum, okay, or vibration spectrum of the gear signal. So this is pitting, you can see. So pitting is a surface fatigue failure of the gear tooth. It occurs when the endurance limit of the material is exceeded. The pit form will cause stress concentration, and soon the pitting spreads to the adjacent region till the whole surface is covered. Okay. So, I mean, mostly it starts at the pitch line. Okay. Because there at pitch line, only single tooth is taking the entire load. Okay. And because of that, there is a very high contact stress which is developed, and then if the case hardening is not proper, then some material will remove from there, and because of the lubricating oil, okay, it gets entrapped between that particular pit, small pit, and then in each cycle, uh, because of the fluid pressure, it keeps on expanding. Okay, so then I mean, it becomes even bigger. So it starts as a very small pit, and if you and it also progresses in both the direction. Okay, in width direction as well as in the profile direction. Okay, so I mean, if you can identify or if you can detect a small pit which has just I mean, just developed. Okay, then probably you can stop this advanced stage of pitting. Okay, so this is the main idea of condition monitoring. Then spalling. Okay, so this is even I mean, it start from the pitting, and then ultimately some flakes will come out. Okay, so the cracking and flaking of particles out of the surface. So ultimately this tooth will fracture, and then I mean, then it will be successively I mean, next tooth will also break likewise. So, I mean, then whole gearbox will fail. So that is the worst case. Okay, but if you can identify these small fitting or cracks, okay, or wear, then probably you can avoid such failures. Okay. So, as I already mentioned, okay, when you are doing condition monitoring, you must understand, I mean, what are the various types of faults which may develop. Okay, so that we already discussed. Then, if you are saying we are doing vibration monitoring, then we must understand, I mean, how the vibration which we are measuring are being generated. Okay, so when we are talking about gear, so you must understand like how the gear vibrations are generated. Okay, so one of the major consideration during the design and manufacturing process of gear is low level of vibration when gears are transmitting power. So of course, I mean, everybody wants that vibration should be as less as possible. Okay, and but even after taking all the necessary precautions, vibration is generated during power transmission. So it means you cannot avoid gear vibration. Okay, so we'll discuss some of the reasons for that. And if the tooth contact force varies in amplitude, direction, or position, so this basically tells you that for any system, not just vibration, if because of the kinematics or for any other reason, okay, if the vibration amplitude is varying, okay, over a period of time, then it will cause uh, vibration. Okay, so if the force which is, I mean, varying, okay, I mean, so amplitude is varying in some regular manner, then it will cause vibration. And if the amplitude is constant, but if the direction is changing, okay, so that also will lead to vibration. And if the amplitude is not changing as well as the direction is also not changing, but its position is changing, then also vibration will be generated. Okay. So all three things are happening. Okay. Any one of them is sufficient to generate vibration. Okay. But in gear, because of a very peculiar kinematic arrangement, okay, the force amplitude is also varying, force direction is also varying, and force position is also changing over a period of time. So it is really difficult to control the vibration in gears. Okay. So now you must be aware, like most of the I mean, automotives and I mean automobile, they are now moving to electric vehicles. Okay. So they are, I mean, having gearbox. Okay. Previously, I mean, for IC engines, okay, vibration level of IC engine was too high. Okay, so that gear vibrations were not that dominant. Okay, but since now there is no IC engine in electric vehicles, there is electric motor only. So that is not generating that much of vibration as compared to IC engine. So, and but in any electric vehicle, gearbox is an integral part. Okay, so now gear vibrations, they have become more. I mean, they need to be addressed more urgently. Okay, so this is how, I mean, gear vibration and understanding of gear vibration, how to minimize it, and also fault diagnosis of gearbox. Okay, that has become very important. So this is like about gear vibration. Okay, so gear vibration can be generated due to design errors, manufacturing error, and operational errors. So these all these things we will see. But the major cause of gear vibration is transmission error. Okay, so if you take any gear pair, it is designed for constant speed velocity. Okay, so like I mentioned, there is a pinion which is having 60 teeth, and there is a gear which is having 120 teeth. So basically, the idea is to get the speed ratio as 1:2. Okay, so we expect that it is constant. Okay, it means when you rotate the pinion by 360 degree, then gear should rotate 180 degrees. Okay, for the arrangement I had discussed. But actually, that is not the case. It is uh, not exactly 1:2. It is sometimes, I mean, if you are rotating the pinion by say 10 degrees, so the gear should rotate by 5 degrees, but it is uh, maybe 5 point, I mean, more than that or less than that. Okay, so that is basically known as transmission error. So there are various reasons for transmission error. Okay, so like tooth geometry. So deviation from perfect involute shape, either by design or manufacturing imperfections or wear. So as I already mentioned that for any gear pair, okay, whether it's a new or I mean, yeah, so or you have manufactured it with very precise manufacturing processes. Okay, so your intention is to get an involute profile to get the constant speed ratio. Okay, so I think you are aware of involute profile. So although we can say okay that we want an involute profile, and there are various I mean manufacturing processes which are able to generate it also on the gears. Okay, but still there will be some deviation from this perfect involute profile. Okay, so this will cause transmission error. And when I mean machine is or the gear is running, then because of the wear, this involute shape may change. Okay, and it will definitely change. So that will further increase the transmission error. And I mean transmission error, it means there is speed fluctuation. It means there is vibration. Okay, then elastic deformation is another thing. Okay, because I'm talking about metallic gears and they are basically having elastic material. Okay, and so when they are transmitting the load, so there will be some bending. Okay, and because of that deformation, there will be some transmission error. Okay, so I mean various factors are there which are responsible for gear vibration, and you have no control on them. Okay, so this is how I mean elastic deformation will cause I mean transmission error. Okay, and then mounting also. Okay, suppose you have if you consider that gear is of perfect involute profile, having a perfect involute profile, and there is no elastic deformation, which is not possible. Okay, still if you assume that there is no deviation from involute profile, and there is no deformation, then maybe because of the imperfect mounting, you will have a transmission error. Okay, because gears are mounted on bearings. Okay, and shafts. Okay, so the configuration of this arrangement is also important. Okay, sometimes because your shaft is, I mean, if you have to mount the gear on some shaft which is quite long, then there will be, I mean, it will be sagging kind of thing. Okay, so because of that, there will be transmission error, and sometimes bearings may have different stiffness, so that may also cause transmission error. So a lot of things are there, okay, which are causing transmission error, and ultimately it will lead to vibration. Then backlash is also provided in gears to avoid this interference, okay, and for better lubrication also. So this is intentionally it has been done, okay, but because of this backlash, uh, it causes torsional vibration, okay, because it may have some impact. Okay, so there will be if the gear is not loaded, okay, and for or the torque which it is transmitting is very less, okay, then there will be some impact or tooth separation. Okay, so that sometimes when your uh, gear is running at lows with low torque, then there is a lot of vibration. But when there is, I mean, when it is loaded, then it runs smoothly. Okay, with less vibration. So there are many things which we have discussed. Uh, so transmission error, then backlash, these all will cause vibration. Okay. then also like you cannot have any gear without having mass unbalance. There will be some amount of unbalance in the rotating mass will be there. Okay, so that will also cause vibration, and then geometric eccentricity also. Okay, so either axial runout or radial runout. So there are many things, okay, which are responsible for gear vibration. Then, so this is, I mean, external excitation means you are this mounting error, then mass unbalance, and then internal excitation, which I already discussed. Okay, like profile variation from the involved profile, elastic deformation. Okay, local Hurtgen deformation. So these are all basically internal excitation. Okay. So now, I mean, we have uh, discussed some of the reasons, okay, or the key parameters which are causing gear vibration. So if you consider that you have no such problem, okay, no internal excitation, no external excitation, no backlash, okay, no issue. I mean, profile is perfect, okay, everything is perfect. Still, gears will have vibration, okay, and the reason is mesh stiffness. So when gear pair they are meshing, okay, so it has been designed in such a way that when one gear is in contact, okay, and before it disconnects, the next tooth pair comes in contact, so that uh, there is no impact. Okay, so that this is the main idea, and this is known as contact ratio, which is always more than 1. So 1.2 or 1.3, and sometimes it may go up to 2.5 or something like that, but always less than 3. Okay, so it is always greater than 1 and less than 3. So whatever it is, when gears are engaging, okay, so the previous tooth pair is always in mesh, and when they are disengaging, the next tooth pair is in contact. Okay, so when, and then there is some time in between, okay, after engagement and before disengagement, okay, there is some time where only single tooth pair is in contact. Okay, so what is happening when gears are meshing? So initially two teeth pair in contact, then single tooth pair is in contact, and then again two teeth pair in contact. Okay, so this is basically uh, giving you a variable mesh stiffness. Okay, so stiffness is nothing but force per unit deflection. So when you are transmitting the same torque, okay, so the force is coming is constant, okay, and when two teeth pair are taking this load, then the stiffness is more, and when only single tooth is taking this, then the stiffness is reduced because deflection will be more. Okay, and force is same, but sometimes two uh, teeth are taking this load, and sometimes one tooth is taking this load. Okay, so this is how mesh stiffness comes in picture, and this is very important. So I have shown here. So whatever I have explained. So if you take this single tooth pair, okay, so initially double tooth pair is in contact, then single tooth pair is in contact, and then again double tooth pair is in contact. Okay, so this is the plot of gear mesh stiffness. So when double tooth pair is in contact, then stiffness is high, and when single tooth pair is in contact, then stiffness is low. Okay, and then again it increases. So you see there is a point where it changes from double tooth pair contact to single tooth pair contact. So there is basically a drastic change in the stiffness, okay, or sudden drop, and then sudden increase. So this change in stiffness okay, will cause high gear vibration. Okay, so if this is more, if this jump is more, then the vibration will be more. Okay, but you cannot avoid it. You can minimize it by just increasing the say contact ratio. Okay, but you cannot totally eliminate it. So I have mentioned various causes of gear vibration. Okay, so you must understand, if you want to control, then also it is important, and if you want to diagnose the fault, then also it is important to understand the gear vibration mechanism. Okay, so now we come to gear fault diagnosis, and I'll be just explaining you one of the very simple method, okay, which is frequency domain analysis. Okay, so using the FFT. Okay, so as I already mentioned, because of there is modulation. Okay, you will find sidebands also. Okay, so there is gear mesh frequency and sidebands. Okay, so let's see how we can use this to diagnose the fault. Okay, so the gearbox vibration spectra normally contains sidebands due to modulation of tooth meshing frequency and their harmonics. An increase in the number of such segments usually indicates the deteriorating condition. Okay, so we'll see what is the system. So we have this gearbox in our lab, okay, which is having this kind of configuration. You can see here there is a pinion and then gear. Pinion is having 32 teeth. Then gear 1 is having 80 teeth. It's a basically two-stage gearbox. So on the same shaft there is another gear which is having 40 teeth, and then it is connected with gear 4 which is having 72 teeth. Okay, so now if you have to do the condition monitoring, so you must understand this system. Okay, so what all frequencies will be generated. Okay, so it depends on what is the input frequency. So this motor will give some, it is the prime mover. So what is the RPM of this shaft 1? And based on that, you can number of teeth and shaft 1 RPM, you can calculate gear mesh frequency. Okay, and similarly for shaft 2 and for shaft 3. Okay, so you can first calculate these gear mesh frequencies and sidebands. Okay, and then you put an accelerometer. Okay, so there is an accelerometer which has been fixed on this intermediate shaft. Okay, housing of this bearing housing of intermediate shaft or shaft 2. Okay, and this is the entire setup. So there's a motor which can be controlled using a motor controller. Okay, and then this is a fixed axis gearbox. Okay, and then there's a planetary gearbox also, and then there is a magnetic brake which is used to apply some load. Okay, and this can be this motor speed and magnetic load can be controlled using some computer control. Okay, so then we have this data acquisition and a 4-channel data acquisition system, and then associated software to get the FFT. Okay, so as I already mentioned, so if you are doing condition monitoring, okay, of any system, then you must mention very clearly what all information is with you. Okay, so spur gear, number of teeth, pressure angle, and module. So material. This is all you can collect And then based on this information, basically we just need the speed and number of teeth for gear mesh frequency. Okay. And we have just inserted, using electric discharge machining, this crack has been initiated. Okay. In fact, it has been induced using this electric discharge machining. Okay. So it has not been done using continuous running it or fatigue test. That we are not done. Okay. So we have induced this crack in one of the one of the gear, okay, which is the pinion, okay. So then the test has been conducted for healthy gear and gear with crack, and the vibration signals were recorded under varying load conditions, like 10 no load and 10%, 20%, 40%, 70%, 90%, okay. And the speed was 30 hertz. Okay, so input speed is 30 hertz. So as I already mentioned, various gear mesh frequency and their harmonics have been calculated. Okay, and then these are the spectrum. Okay, vibration spectrum, and we just observed like what is the gear mesh frequency, amplitude, and what is the sideband amplitude. Okay, so these EMS frequency and sidebands we were observing for various load conditions. So you can see at A is spectrum of at healthy gear, okay, at no load, and B is a cracked gear. So left side, left side figure is for healthy gear and right side is for cracked gear at various load. So this is for no load, and the speed is constant 30 hertz. So next figure is for 10% load. Okay. Similarly, the top left figure is for 40% load, healthy gear, and top right is for 40% load and cracked gear. So likewise, okay. Then we compile this information, that what is the effect of load and if there is crack and if there is no crack. So we studied the sidebands only. Okay. So these sidebands you can see here. LSB means lower sideband and HSB is for higher sideband. So as I already mentioned, there is a gear mesh frequency which is 953, okay, hertz, and then lower sideband and higher sideband we have observed, okay. And then you can see if gear is healthy, okay. So there is no change in the sideband amplitude, okay. But when there is a load, 10% load, then we increase to 20%, 40%, 70%, 90%. So lower sideband for cracked gear is increasing, okay, rapidly as compared to for the healthy gear. So for healthy gear also it is increasing, but not that much as compared to the cracked gear. Okay. So this is how, we can say that if you are observing the sideband and if its amplitude is increasing, okay, it means there is some crack which has been developed. Okay. Similarly for right hand sideband, it is also increasing, but not that much. Okay. So with the load, so if there is a crack, then amplitude is even higher. So if you are just observing the gear mesh frequency, sometimes you will not get the information because of the modulation. The most of the energy is then transferred to that frequency band. Okay, so you can find something like more, sidebands are more informative as compared to mesh frequency for diagnosing the fault. Okay, so this is the conclusion for this study, that frequency spectrum has been analyzed critically for the sideband activities around gear mesh frequency for normal and cracked gear, and it is observed that at a particular speed and for low load condition, the amplitude of sideband is lower, and as we go on increasing the load, the magnitude of sideband also increases significantly. And yeah, so this is how it has been done. Now, here we had just used very simple signal processing technique, or which is known as FFT, okay, fast Fourier transform. But now, that is sometimes just sideband. They don't contain the information of the gear fault. So we need to perform some advanced signal processing technique. Okay. So like empirical mode decomposition, continuous wavelet transform, and likewise. Okay, so we'll just go through that, and we'll see. We'll also see like how some artificial intelligence technique can be used for artificial neural network can be used for fault detection. Okay, so as I already mentioned, like you must first see like what are the various types of faults which may develop. So like pitting, and then wear, crack, scuffing, swelling. Okay, so these are, I think, and the missing tooth. So this is, very severe case, chipped tooth and missing tooth. So this is also, sometimes even if it has developed on just one gear, some chipped tooth, and if you can detect it, it can it can stop the catastrophic failure of the entire gearbox. Okay, although it is possible, you must try to diagnose or to detect the fault as soon as possible. But sometimes, even if you are detecting the small, if the tooth has been chipped, okay, some part of the tooth has been removed. So then also, even up to that stage, also, even if you can detect it, that is fine. Okay. So, like here, if you have some idea of some signal processing techniques like continuous wavelet transform. So it is a time frequency analysis. Okay. So here, because sometimes what happens in any system which is having amplitude and frequency modulation both. Okay. So you need to know what is the frequency component at what time. Okay. Because in FFT, you don't know that which component is present because it gives you the information at the particular time. Okay, so at that particular time, what frequency components present, that is fine. So if you are analyzing FFT for some given time, then probably you may miss that frequency component. But when you are doing time frequency analysis, then you know what frequency is present up to what time. Okay, so that's why various time frequency analysis techniques are available, and this wavelet transform is very effective. Okay, and we are using any software, even MATLAB also they have inbuilt functions, so it is very convenient to use these tools. Okay, so here you can know from the time domain signal what are the various frequencies present, and up to what time it is present. Okay. And then empirical mode decomposition is another signal processing technique where you are basically doing some, using this algorithm. Okay, I'm not going to explain it. So you have to take the maxima and then minima, take the average, subtract it from the signal. And I mean, this process, I mean, a lot of people, they have used this, but this basically what it does is it if you take a time domain signal which is having various frequency components, so it will uh, decompose that signal according to uh, frequency bands. Okay, so from very high frequency band to low frequency band, or basically the residue, which is a monocomponent signal. Okay, and which further you cannot decompose. Okay, so this is how I mean this algorithm works. So essentially, I mean you have a time domain signal from the given time domain signal, but in various having various frequency bands. Okay, and why it is important to do this kind of decomposition, because the fault information is present in a particular frequency band. Okay, so if you can segregate those frequency bands, and then if you work on, I mean, if you analyze a frequency band which is having the information of the fault, okay, because all faults are related within one particular frequency band, okay, and then probably, I mean, you are not, I can say, I mean, your signal to noise ratio will be better, so you get a better information, okay. So that's why these kind of signal processing techniques are required. The main idea of signal processing or advanced signal processing technique is to basically take care of the both the components like time and frequency. Okay, which was, I mean, which is not possible with frequency transform only. Okay, or FFT only. But still, I mean, industry people are using FFT, and it is sufficient to in most of the cases. Okay, but if you are doing research and if you want to develop, I mean, even more accurate methods, then definitely these kind of advanced signal processing techniques are important. Then even a step further, you need some like classification techniques, okay, so that you can automatically say that whether some fault has developed without having human intervention. And nowadays, I mean, a lot of focus is on AI and ML, which is artificial intelligence and machine learning. Okay, and they are successful also. Okay, so I mean, various neural networks are available, and this multi-layer perceptron is basically a feed-forward artificial neural network, and this consists of at least three layers. Okay, input layer, hidden layer, and an output layer. And except for the input node, each node is a neuron that uses a nonlinear activation function, and then this MLP utilizes a supervised learning technique called backpropagation for training, and its multiple layers and nonlinear activation distinguish MLP from linear perceptron. Okay, and yeah, so this is the architecture of this multi-layer perceptron network. Okay, so you have various input like X0, X1, X2. Okay, and then there's how they are connected, and then I mean based on the training data, there is some. I mean, you can conclude, you can classify. We'll see. So I mean, we have used it, okay, but as such, just as a tool for classification. We have not done anything in this multi-layer perceptron network. That is not the focus. The focus is to get the right signal. That is, as a, I mean, if you are doing condition monitoring, okay, so the first step is how you are getting the data. That is very important. Okay, and how early you can detect the fault. That is another important aspect. Okay, so we already seen like in one case crack, okay, for one particular gear system we have seen, and that by using FFT analysis only. But now we'll, study this wear, because wear is also a very dominant thing. I mean, it is a very uh, most of the failure they occur because of this wear. 55% we can see, or you can say surface deterioration 70%, and out of that 55% due to wear and 15% due to corrosion. And then wear also mostly because of adhesive wear, okay, and abrasive wear. So we have taken a case of abrasive wear, okay, and this is, as you can see in the figure 3, okay. So this gear is having some abrasive wear, which I will just show you here. So yeah, this kind of wear. So this is abrasive wear. So we generated, this is from some source, okay. But I mean, this is classified as, this is basically abrasive wear. So we developed this kind of wear using some of the laser machining technique, okay. So I will just show you that, okay. So yeah, we created abrasive wear, okay, and this is our experimental setup, okay, and this is this is having a motor which is connected with some shaft, and then there is a belt and pulley arrangement, and there is a bevel gearbox, okay, and then we run it at various speed, and then for various load conditions, okay. And these are the, if you're doing condition monitoring of any system, so you must understand what are the various components which are there, okay. And then, yeah, so that is basically a bevel gear, okay. So this test was done on bevel gearbox, okay. And this is, you can say A, B, C, D, these figures. So we have this laser cutting machine, and with that we remove the layers, okay, from the surface of these bevel gear, okay. So you can see here incipient, and the depth is 22 microns, okay, so very less. Then we further increase the depth by increasing the number of passes and the power of the laser, okay. So in a very controlled manner, we remove the layer one by one from the surface, okay. And the depth of these where you can see is varying from 22 micron, which is quite less, to 33 microns, 39 microns, 47 microns, likewise. Okay, so these we are considering 4 cases, okay, so of wear: incipient, slight, moderate, and severe. Okay, so this is how experimentally we are trying to generate a wear in a controlled manner. Okay, so measurement is also important of these kind of small material removal. Okay, and you cannot do it with simple apparatus. So we have this optical microscope. So with that we could measure, okay, the depth of these. Okay, laser is doing material removal, okay, and then we are measuring it with some advanced equipment. So why I'm mentioning this, because these are very important when you are doing any research. So it should be in a controlled environment, okay, and your measurement should be accurate. So that's why I focused on accelerometer which you are selecting, you must understand how you are selecting it. Okay. And then if you are studying any fault, then how you're creating it. Okay, either if the best way is to do it in fatigue test. Okay, whatever it is not possible, then how you are generating it, that is also very important. If you have equipment, very sophisticated equipment, then you can do it. Okay, so we have used all such things, and then these kind of classes, I mean, these kind of where fault we develop, okay, incipient, slight, moderate, and severe. Okay, so now I think I explained you what we mean by various classes of fault. Okay, so this is the methodology. First for healthy gear, then incipient wear, then slight, then moderate, and then severe. These are the five basically classes you can say. Okay, then we applied empirical mode decomposition. Then we obtained the component, okay, which is known as basically IMF, okay, intrinsic mode functions. And then we calculated features, and then used Kruskal-Wallis test to obtain the statistically significant feature, okay, because a lot of features we have, then we have to just significant features, okay, and that we classified using, we obtained using this Kruskal-Wallis test, okay. Then using multi-layer perceptron network, we tried to classify it, okay. So this is what is the methodology, okay, and these are the obtained signals, okay, A, B, C, D, E, which are basically healthy gears, healthy gear signal, then incipient wear, then slight wear, moderate wear, and severe wear. So for all these classes, we basically captured the signal, okay, and these are the time domain signal, and then I mean, this is for various load and for various speed. I've just shown for one load and one speed, okay, and then various features like kurtosis, standard deviation, skewness, root mean square, crest factor. These are normally used, fault indicator, you can say, or features. Okay, so we calculated these things. Okay, then yeah, so for various components like IMF1, IMF2, IMF3, 4, 7, 8, we calculate kurtosis, skewness, standard deviation, root mean square, and crest factor. Okay, and then using this Kruskal-Wallis test, which is having probability less than 0.05, okay, for all the signals like healthy gear signal, incipient, and yeah, so based on that, we can identify which are the statistically significant features, okay. Then we took only those features, okay, and then using this multi-layer perceptron network, we could find out, I mean, if you are just taking kurtosis as input feature, then the classification accuracy is 77.5%. Then if you're just taking skewness, then what is the accuracy? Almost same. Okay, then standard deviation only giving 82% accuracy. RMS only giving us 82% accuracy. Plus factor giving us 69%. Okay, and when kurtosis and skewness both are taken as input feature, okay, then frequency accuracy is classification accuracy is 88%, and when kurtosis, skewness, and standard deviation is taken, then it is classification accuracy is close to 90%. But when we further take, I mean, kurtosis, skewness, standard deviation, and RMS, it has reduced to 82%. Okay. So, I mean, this is a step forward for classification. Okay, but the important part here is to uh, perform the experiment in a right manner. Okay, and then collect the signal like this vibration signal. If you are not able to collect them, or if you're not acquiring them in a right manner, then everything will be of no use. So then further you perform some statistical analysis or like features, various statistical features and kurtosis and standard deviation, RMS, all these people are doing, okay. And most of the time they can be used for identification of the fault, okay. And then if you're using some neural network kind of thing, then that can also classify. And then you have to uh, try various input features, and some of them will give you better accuracy. So you can propose that, okay, this can be used as a classifier. Okay, this is how, I mean, uh, now products or I mean in industry, I mean a lot of people are developing AI based product. Okay, so they can do many things. Okay, but that is not our main objective here. Okay. So the iterative EMD method has been used to decompose the gear vibration signal. And okay, so I think I have already mentioned these things. Now we had another case of class, I mean, just to see whether the cracked, chipped, and missing tooth. Okay, so these are the three different. Instead of progressing a particular fault, we took three different kinds of faults: uh, cracked, chipped tooth, and then missing tooth. Okay, and this is the methodology. So first acquire the vibration signal, and you also, I mean, in this we have also taken tachometer signal. Then some, okay, after taking the data, we did independent angular resampling. Okay, I will just explain it why it is important. Then angular domain averaging. Okay, and then continuous wavelet transform. Then again, some artificial neural network, okay, backpropagation neural network to classify healthy, cracked, chipped, and missing. So this is, I mean, we acquired the machines. I've already told you the experimental setup. From there, we acquired this vibration signal and then perform this independent angular resampling technique. Okay. Uh, this is for, I mean, fluctuating speed. You have to resample the acquired signal, okay, or the number of samples or sampling frequencies has to be changed, okay. And then this has been done in the angular domain. It means you are taking a reference signal, and for each revolution, you are capturing the signal, okay, and then convert it into continued, I mean, CWT, which is continuous wavelet transform, and from there, some coefficients, I mean, wavelet coefficients have been generated and they have been used for neural network input. Okay. So this is the concept of independent angular resampling. So this is one of my students who worked on this, and it's a novel method. It is assumed that the angular acceleration remains constant during each independent revolution, and to determine the constants, the instants of time at three different angular positions are required. Okay, and an additional reflective strip is mounted at 110 degrees from the reference. So basically, using the tachometer, okay, for each revolution, three times, I mean, a signal has been captured. Okay, so instead of taking a continuous signal, although it's a continuous process, but we are dividing it into three parts using three different reflective tapes, okay, and using a tachometer. So then, I mean, I'm not going to explain it in detail, but using this angular resampling and taking the signal in angular domain, okay, and then doing its averaging, it is better idea for denoising of signal, okay. So then this again, this neural network has been used, okay. And then, yeah, this is, I already explained, this is the experimental setup, okay, and how where the tachometer is and where the accelerometer is, all these things are mentioned. So yeah, so from time domain signal, which is converted into angular domain average signal, and then its wavelet coefficient being calculated, and then both noise, I mean noise signal as well as I mean microphone is also used in this study, and this is the architecture of ANN, number of neurons in the input layer, 360 number of neurons in the hidden layer, 9 number of neurons in the outer layer, 4. And then based on this, yeah, so various cases like when only sound signal is being used, when vibration signal is used from different locations. So different locations were there just to see the effect of location. Okay. So, I mean, test accuracy for cracked gear is 100%, for chipped gear is 100%, broken 97.4%. For vibration signal, for cracked gear, accuracy is 100%, chipped gear again 100%, and for broken, it is now 97.4. So it means, yeah, it is quite accurate method because the fault level was also quite high. Okay, so this accuracy is possible because your input parameters are quite distinct from each other. Okay, so this is how, I mean, uh, you can do fault diagnosis. Okay, so in this work, a web propagation neural network using continuous wavelet coefficients in the form of input feature vector is employed. Okay, so anything else can be used for this. Okay, so this is all, I mean, the way you can uh, develop some product, okay, where you just need one input and then you can tell that these are the this is the stage of fault. Okay, so this, I mean, this can be customized for a given gearbox. Okay, so I'm not aware, maybe such things are already in the market uh, where you can just put one sensor, okay, uh, on the gearbox of your interest, okay, and then it will give you the information whether there is some crack or, I mean, it will specifically mention that these are the, I mean, this kind of fault has been developed, okay. So this is all, I mean, for the discussion about ear fault diagnosis. Okay, and so I think is this okay? And I have one more presentation, or if you want, we can stop and then we can have some discussion for around 10-15 minutes. Or shall I start another presentation?
Yes, sir, you can.
So I mean, the discussion questions are not required at this point of time. From the audience, you can ask them if you have, if they have any question, they can ask. Then we can move to the next.
Yes, I have dropped the message and I'm waiting for the participants to ask you put up questions. So I'm waiting for their response.
Okay, okay. So meanwhile, I change this. What happened?
Right now, participants who are there online, they can
Ah,
put up their question in to Professor Parey by dropping their questions in the chat box. Please, if from the audience or the participants, if there is any question, please, you are here being encouraged to ask the question to the professor. I think, sir, that there's no question in the chat box, so I I would like to thank you, sir. We are very much thankful to you, Professor, for taking time for us out of your busy schedule and enlightening us with an important aspect of condition monitoring related to gearboxes.
thank you.
Am I audible, sir?
Yeah, am I audible?
Yes, sir. You are very much audible.
Okay, so thank you very much. So I will just share, I mean, one slide which the facilities which we have at IIT, okay? Just because whatever I have shown in my presentation, because we have a center which we call.
Sorry to interrupt you in between. Sir, here we have got some question.
Okay, okay, fine.
I would like to share with you some queries from our participants.
Okay.
Here we have a question for you, sir. How far the trend of machine failure can study using simulation model? From L.R. Chandran.
Can you please repeat the
Yes, sir.
question?
Yes, sir. Sure. How far the trend of machine failure can study using simulation models?
That simulation model will give you the information according to, I mean, first you have to model for a healthy system, okay? Then you can say, okay, if you are having a healthy system, then this will be the amplitude of, say, vibration, okay? And if there is fault, then this will be the, if there is this, say 1 mm crack, if it is 2 mm crack, 3 mm crack. So definitely, I mean, you can predict, okay, that if in presence of fault, what will be the response, okay, or how much vibration will be generated. Okay, that is possible. But then this has to be validated experimentally. So only experimental signal, okay, if you are capturing the signal and then for various faults, if you are measuring the vibration, then you can say, okay, yes, it is, valid. Okay. So, I mean, what is question is actually trend, how simulation can be helpful. Okay. So yes, in that sense, I mean, if you are just if you are comfortable, I mean, if you have verified your modeling thing, okay, then probably if you capture the signal and if it is in that range, then you can say yes, some fault has been developed. So I mean, yes, first you have to verify your simulation experimentally. Then for any, I mean, for the similar system, you can say, yes, if vibration level is this much, then probably this is the, there is some fault.
Okay, thank you, sir. Next question is from Kulkarni PG. Energy, entropy, PS and R, can they be used in the place of wavelet coefficients?
Yes, yes. I mean, you can develop your own fault indicator. So a lot of work is done on developing your own indicator. Okay. So yeah, definitely you have to basically you have a time domain signal, okay, and how you are converting this time domain signal into some useful information, okay. So like kurtosis and this R crest factor, these are a very common thing, okay. But now energy based operators are also there, and then if you put them for, I mean, as a input feature, then I mean, definitely if you come with some feature which is better for classification, then sometimes energy based feature may be useful. Sometimes statistical feature only they are okay. Okay. So I mean, yes, you can explore. I cannot comment on that this is going to work better, but yeah, wavelet coefficient based or EMD based or yeah, so you have to try. Okay.
Okay, so next question is from Barrett ME. For mathematical modeling, differential equations are developed. Some has considered TVMS and some have considered as a pulse.
Yeah, so my comment here is TVMS is more accurate. Okay. So time varying mesh stiffness one should use for dynamic modeling.
Okay, sir. Sir, next question is from Pratik Muradia. Mr. Pratik Muradia, which condition monitoring technology or predictive maintenance technique can be used in SME where they cannot afford costly equipment? How would you suggest SME should move in the direction of PDM?
Okay. So I mean, first thing is whether it's MSc or whatever industry. Okay. I mean, first thing is you have to make a plan. Okay, how much? First of all, whether you have some critical machine or not. Okay, so first thing is you have to identify the critical machine, and then you have to assume like if you if suppose that machine stops, okay, then how much loss it will incur. Okay, and then suppose say if every year you are losing say 20 lakh rupees from that critical machine, okay, if it stops or if based on its history, okay, then probably you can say, propose this thing to the management that okay, if we invest say 5 lakh rupees, then probably we can save 20 lakh rupees per annum. Okay, so that model has to be, I mean, that analysis has to be done. And I mean, if you are doing vibration monitoring, I mean, I cannot say you can use vibration monitoring everywhere, okay? But if you it is applicable, then I think nowadays you can start with even 5 to 7, 8 lakh rupees only. Some basic vibration monitoring thing can be done. So a lot of I mean, indigenous solutions are available.
Okay, sir. Sir, one participant has asked a question. As you have discussed about Kruskal-Wallis test, so what other feature ranking techniques would you suggest to be used for fault classification in machine learning domain from Stratif?
I mean, this is one method, okay, and I mean, this is a lot of others are available, okay. I cannot comment on that right now, okay. But this one, student, they have used this one, Cuscus was test. So various statistical techniques which are there, you can explore. Okay, I cannot name them right now, but yes.
Okay, sir. The same participant has added another query, sir. If is it possible for comparative analysis to use multiple techniques to identify best feature for fault classification?
Yes, yes, it's always better if you are using two techniques. So that may be like vibration and acoustic signal sometimes, okay? Or say uh, people are doing with this wear debris monitoring also, okay? So, I mean, It is always better if you are using, I mean, two different techniques which are giving you individually a good result, and when they combine, then probably you can get even better results.
So, sir, these are the queries which we were having from our participant sites. So, we are done with the queries. So, on behalf of, if you say you
Yeah.
want to say something.
Yeah. So my screen is visible.
Yes, sir. Yes, sir.
Yeah. So I'm just showing the facilities which is available at IIT Indore, and because of these facilities only we can do various, I mean, experimental work. So this is the roughness measuring equipment. Okay, so if you want to study, say, what is the effect of surface roughness on gear vibration, okay, so this machine can be used. Then we have a lot of manufacturing facilities also available. So wire EDM. Then for noise analysis and vibration analysis, we have various transducers and data acquisition system. And like transmission error I mentioned for, so transmission error, we have this dual flank roll tester. So it can be used for measuring the uh, transmission error. So we can study effect of transmission error on gear fault diagnosis. Okay, then we have some manufacturing facility also. Okay, gear hobbing machine, and then bevel gear cutting machine. Then we have for measurement like CNC gear metrology. This is a very important machine, and very few IITs or maybe very few institutions are having this, where we can say, as I mentioned, so the gear profile, whether it's involute or not, so that can be verified in this machine, okay, which is CNC gear metrology machine. Okay, and then this is manual. Okay, this is the manual gear metrology machine. That was CNC, and this is manual. Then we have various optical uh, machines. Okay, which is used for measuring the surface profile. Okay, and this is, I think, CMM. Okay, I think this is, and then contour tracer, tool makers microscope, height gauge. So, I mean, a lot of metrology facility we have. Okay, a lot of manufacturing facilities we have: CNC, wire EDM, CNC EDM, CNC milling, CNC turning, micro machining, 3D printing, and this is fault simulator. So, using all these machines, we can, I mean, create various faults, and then we can measure them. And this machinery fault simulator we use as a test rig. Okay, so this is just I wanted to show you. Yeah, thank you.
Okay, sir. Thank you very much. Thanks a lot, sir. We are very much thankful to you for taking time for us out of your busy schedule and enlightening us with an important aspect of condition monitoring related to gearboxes. Thanks a lot, sir, once again.
Thank you very much for giving me this opportunity, and all the best to all the participants and everyone. Thank you.
Thank you, sir. Welcome.